rotational motion. Now, when a body rotates, say we have a body rotating about an axis. When you have a body rotating about an axis, so this is an axis AB about which the body is rotating. Then if there is a particle, say here you have a particle P, a particle Q, a particle R. Now when this body is rotating about this axis, this particle P moves in a circular motion. This Q moves in circular motion. R also moves in circular motion. So when a body rotates about a particular axis, then each particle moves in circular motion. Each particle moves in circular motion. Now, in the time P moves in one particular circle, in the same time Q moves and comes over here. That means all the particles covered this 360-degree angle in the same time. So in in rotational motion, children, angular velocity omega, which is rate of covering angle, is same for all particles. This is very, very important. Omega is same for all particles. Why? Because in the time P moves this 360-degree angle, in the same time Q moves that 360-degree angle. But they are covering different distances. P is covering, say, 2 pi r1. R1 is this radius of P. If Q is moving in a radius r2, then Q will be moving a distance 2 pi r2, and R will be moving a circumference 2 pi r3. The distance covered by them are different. The distance covered by them are different, but the angle is same. So we can say that although angular velocity is same, but linear velocity is different for the each particle. Why? Because they are covering different distances, or you can say v is r omega. R is different, so velocity will be different. So in rotational motion, we can say that each particle moves in circular motion and each particle has the same angular velocity. Now, like linear motion, the equations which we had, v equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. Here we have similar type of equations. Final angular velocity is initial angular velocity omega naught plus alpha t. Alpha was my angular acceleration. Here the angular displacement is theta. Theta equal to omega naught t plus half alpha t square. Here you have omega square equal to omega naught square plus twice alpha theta. Theta is my angular displacement. So, in rotational motion, the equations are modified as omega equal to omega naught plus alpha t, theta equal to omega naught t plus half alpha t square, and omega square is equal to omega naught square plus 2 alpha theta. Now, in rotational motion, to rotate a body, we need a torque. Say, this is my body and it is rotating about this axis. I consider 3 points P having radius say R1, Q at a distance R2, R at a distance R3. Now as this body rotates about this axis AB, I need a torque to rotate them. Say the torque here acting on P, torque acting on the particle P is force into perpendicular distance. Torque acting on particle 2 is, we consider a force F2 acting on particle 2 Q. The torque is F2R2 because the distance from this point is R2. Torque is F into D. Similarly, the torque acting on particle 3, if this is F3, it is F3R3 and so on. Now this force can be written as mass m1 into acceleration the acceleration can be written as dv1 dt. Now just now we said that for all particles omega is same. This is very important. We know V is equal to R into omega. Let me rub this a little bit. I will write this again. Now this can be written as m1 ddt of v1 can be written as r1 omega. R1 is constant for particle P. This is for particle P. So I'm writing this as m1 r1 square d omega dt. Similarly for the second particle it will be f2r2. And if this is solved then this can be written as m2 r2 square d omega dt. Omega is same. Mind you, this is also omega, this is also omega, because for all particles omega is same. Now I move for r, for particle r. What is my torque? It is F3R3. So this can be written as M3 R3 square. This can be written as M3 R3 square. Again d omega dt. Omega is same. Omega is same for all particles. So to rotate this body, to rotate this body what is my total torque? Total torque is tau 1 plus tau 2 plus tau 3 dot 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 dot. So this is written as m1 r1 square d omega dt plus m2 r2 square d omega dt plus m3 r3 square d omega dt dot 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 dot. So this is the torque acting expression for torque. Now if I take d omega dt common, if from here d omega dt is taken common, it is m1 r1 square plus m2 r2 square plus dot 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 dot. Now this term m1 r1 square m2 r2 square, this is known as a very, very important term. I, I is very important. I means for me, isn't it? This I is called moment of inertia. M1R1 square plus M2R2 square plus dot 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 is very important, and it is called moment of inertia. So my torque now becomes I d omega dt. D omega dt is nothing but angular acceleration. So this can be written as I alpha. So torque is I alpha. Try to memorize it. Torque is I alpha. I is the moment of inertia, which is m1r1 square plus m2r2 square plus dot 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 dot. Another term which we will be needing very often is angular momentum. Capital L. The same body, if you consider, it is rotating about this axis. I have point P, Q, R. P has velocity v1, so linear momentum p1 is m1 v1. Q has velocity v2, so linear momentum p2 is m2 v2. R moves with velocity v3, so linear momentum p3 is m3 v3. This body is rotating about this axis. Angular momentum is linear momentum into perpendicular distance. Now this distance is r1, this distance is r2, this distance is r3. Angular momentum of particle 1 is P1 into R1. P1 is mv, m1 v1, and v1 can be written as r omega. This v1 can be written as r1 omega. So this becomes m1 r1 square omega. Again, remember, omega is same for all particles. Now, angular momentum of particle 2 is P2R2. So this can be written as M2 R2 square omega. Omega is same. Angular momentum for particle 3 is P3R3. This can be written as M3 R3 square omega. So my total angular momentum is L1 plus L2 plus L3 plus dot 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 dot. So this is M1 R1 square omega plus M2 R2 square omega plus M3 R3 square omega plus dot 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 dot. Now if I take omega common, if I take omega common from here, we have m1 r1 square plus m2 r2 square. Again that very important term is coming. This is I. I is very important, moment of inertia. It is called moment of inertia. So my angular momentum becomes I omega. Angular momentum becomes I omega. From here, we can understand law of conservation of angular momentum. Now, we had torque as I alpha or I d omega dt. And from here we have angular momentum L as I omega. Now if this is differentiated, dl dt is I is constant, d omega dt. So this is I alpha, and I alpha is nothing but torque. So this can be written as torque. So from these two expressions we can say torque is rate of change of angular momentum. And law of conservation of angular momentum tells us that if torque acting on the body is zero, then dl dt is zero. In that case, angular momentum will remain constant. And what is angular momentum? I omega. So from here, what can we say in this case? Product of I and omega will remain constant. Now let us take an application of this. Say, we have a man standing in a table which is rotating. You have a man over here. He is standing with his hands outstretched with two heavy weights. And this table is rotating. It is a rotating table. Now this distance from the axis of rotation is capital R. This is my axis of rotation. Now, what was my moment of inertia? Say if this is my body and this is my axis, this is M1 at a distance R1, M2 at a distance R2, M3 at a distance R3, M4 at a distance R4. Moment of inertia of this body about this axis AB, IAB was M1R1 square plus M2R2 square. This was moment of inertia. Now here what happens, this man when he pulls his hand inside, when this man pulls his hands inside, the distance of the heavy weights from the axis decreases. R decreases. Now if R decreases, what happens? From here, I will decrease. But from the top, here there is no torque. So I into omega should remain constant. So if this is moment of inertia I1, omega 1, and for this one my moment of inertia is I2, angular velocity omega 2, so I omega should remain constant. So what happens? I1 omega 1 is equal to I2 omega 2. Now this I2 becomes less. Why? Because R decreases. So I2 becomes less. But the product of I and omega is same. I2 becomes less. But the product of I and omega is same. So what will happen? Omega 2 will increase. So all of a sudden, we will see the man moving fast. We will see the man rotating fast. Omega 2 will increase. All of a sudden, we will see him rotating fast. Omega 2 will increase. It is for the same reason in Olympics, while diving from in a swimming boat, the person pulls his hands and legs close together to his body to reduce the moment of inertia and to increase the angular velocity so that he can give a greater number of volts. Now, what is the work done in rotation? We have understood torque, we have understood angular momentum. Now, what is the work done in rotation? Now, when a body rotates, the small work done dW is the tangential force into displacement ds. Now ds can be written as r d theta. Now tangential force into r is nothing but torque. So this can be written as torque into d theta. So my total work done, I have to integrate this from 0 to theta, torque into d theta. So torque is this is d theta. If you integrate d theta, it becomes theta. Limit is from 0 to theta. So when you put the limit, it is upper limit minus lower limit. So the work becomes torque into theta. So now my work becomes torque into theta. My power is work by time. It is the rate of doing work. So this can be written as torque d theta dt, because from here dw is torque into d theta. Now d theta dt is nothing but omega. So power can be written as torque into omega. And what is the kinetic energy of rotation? What is the kinetic energy of rotation? Net kinetic energy is, say it is half m1v1 square for particle 1, half m2v2 square for particle 2, m3v3 square for particle 3, and so on. Now we know a very important point of rotational motion is omega is same for all particles. So this can be written as half m1, v1 is r1 omega, omega is same for all particles, v2 is r2 omega, and so on. Now if I take half omega square common, I end up in m1 r1 square plus m2 r2 square. And here is again the most important term, I, moment of inertia I. So kinetic energy of rotation is half I omega square, half I omega square. Now if we analyze the expressions and find out the difference between translational and rotational, the expressions. Say, here I write down the physical quantities. Here I write down the translational values. And here I write down the rotational values. So here I have the physical quantities. Here I'll be discussing the translational which we know from before. And just now, an analogy what we are going to analyze, rotational. So from the beginning, first point, displacement. My translational was S, rotational was theta, and the relation between them was S is equal to R theta. Next point we move to velocity. Velocity V was ds dt. Angular velocity omega is d theta dt. And what is the relation between them? V is equal to R into omega. Next point is acceleration. Acceleration was dv dt. Here angular acceleration was d omega dt. And the relation between them is A is equal to R alpha. Now, fourth point is momentum. Linear momentum P was mv, angular momentum L was I omega. Mind you, children, in this mass is actually a measure of inertia, and hence in analogy this I is called moment of inertia, which was summation of all the mi ri square, I equal to from particle 1 to particle n. Fifth point was force. This was my linear momentum. This was my angular momentum. This was actually my angular momentum. Now for force, here we know force is mass into acceleration. Again we know force is rate of change of linear momentum. If force is 0, then dp dt is 0, p is constant, linear momentum is constant. This was called conservation of linear momentum. In analogy, what we have here? We have here torque. Now, torque here is I alpha. Instead of acceleration, here we have alpha, and instead of mass, we have I. Now, again we know torque is dl by dt. If torque equal to 0, then dl dt is 0. Angular momentum is constant. This is called conservation of angular momentum. Which tells us that product of I and omega should remain constant if there is no torque. Other than this, what we have learnt? We have learnt what is work. Work for translational motion is force into displacement, and for rotational motion, work is torque into angular displacement. We have also studied what is kinetic energy. Kinetic energy for translational motion is half mv square, and for rotational it is half I omega square. Half I omega square. So this kinetic energy is half mv square, and this is half I omega square. So these are the formulas which we have to memorize for doing the basic sums of rotational motion. Now in rotational motion, what will be troubling us is this I factor. It will be this I factor. Everywhere we have to calculate I and then do the sum. So we have to learn how to calculate I of different bodies about different axes, then sums will become easier. So in my next video, I am going to give you how to calculate moment of inertia of simple bodies about different axes.